What are the various strategies for addition by counting? In the video we have within the capsule, we see some children that are adding, and they use various strategies. We can identify two of these. So what they do is add 3 to 4 from what we've already developed by counting, right? But they do it in a different way. There is a student that counts the first 4, and then she counts the other 3, and then she says 1, 2, 3, 4, 5, 6, and 7. In this strategy, let's say there are 2 sets. The initial and the first and the second. This is a correct strategy, but we always try to encourage students to develop a slightly more elaborate one, even if it is counting. I already considered the 4 to be an object, let's say. That is, that by encapsulating it, the 4 is already here. And from that 4, we always say to the children that they keep it in mind, and then count 5, 6, and 7, but without counting the first 4. We associate that with the 2 basic counting strategies of adding by counting everything and counting from after the first one. Show us some situations in which we use known facts to work out the result of a sum. We need to be very aware that we construct the sum based on counting. I mean, children do their first sums by counting. As we said, by counting the 2 sets or just the first one, they take it as an object and count the second. But long term, we only want these to work as a crutch, which we can take away at some point down the road. Our aim is that when students get to a higher grade and we give them an addition, such as 6 plus 7, it isn't necessary for them to hide their fingers underneath the table in order to do the addition. Not because we don't want them to hide it, but because we want students to use other skills to do sums like this. Because in the long run, counting is inefficient. Our aim is that they use the other basic strategies that we have for addition, not so much counting, but working it out through facts. In this video, we have 3 examples of 3 children doing additions by deducing the facts. We have a boy who uses a fact that he is familiar with. He knows 3 plus 3 equals 6, so he says, if I have 4 plus 3, it means I have 1 more, so I have 1 more than 6, so I have 7. And another boy who also uses a sum he knows, also with doubles, but with 4 plus 4, which he knows is 8. And again, in the second set, instead he can say, instead of 4, I have 3, so 4 plus 3 is 1 less, which is therefore 7. Finally, a girl who doesn't use doubles, but she relies on another fact that she knows, which is that by using the 5 fingers on one hand, we can do many sums that use up to 5 almost without realizing it. When I teach the children to use their hands like this, they don't count finger by finger. They already know that there are 5, and they see that with 3 here, now there are 8. So on the basis of a question like that, the girl thinks, if I have 4 plus 3, then I take 1 away from there, and there are 5 plus 2. That's her way of reasoning. 4 plus 3 is the same as 5 plus 2. So if 5 plus 2 equals 7, which I know from memory, 4 plus 3 will also be 7. And these ideas that these children have are such important ideas that we give them lots of praise when they use them in class. And we encourage their classmates to copy their reasoning, which we consider very efficient, and to learn how to add. So the basic idea is that we add by counting or by using facts to add, and we practice this specifically to develop it with the students. Sometimes they use facts to add so quickly that we don't realize it because we ask a student 4 plus 3, and they immediately say 7, even though they have worked it out through 6 or 8. Because the chain of deduction becomes increasingly short, so it's hard to tell whether the child has worked it out or used a known fact. What we have to do is ask them in that case. It is very important because, according to teaching research, students this age are often much more successful at math when they have a good capacity for deduction. Even if they have just a few known facts, if they have good rules of deduction, they can apply the few facts they have and get a lot out of deduction. And that's why the strategies used by these 3 students, for us, are extremely relevant. And we emphasize them here in this capsule. But above all else, we emphasize and encourage them in all of our classroom discussions. What type of problem is an addition problem when one of the numbers is covered? The situation we'd use as context for students would not be from real life, but through the use of interactive materials in the classroom, so that we can see both sets of numbers in front of us. We can't see one of them, but the fact that we can't see it is exactly what helps us to develop or to encourage counting strategies in which only the second set is counted instead of both of them. But this kind of problem, like the one we have here, is clearly a combination problem. Because a transformation problem is one where there are 4 cubes on the table, and then the teacher gives you more cubes separately. So in this case, the fact that they are covered should not be confused with the fact that within the Carpenter classification of problem types, this is a combination problem. What formulations illustrating the following types of calculations can we propose? For the kinds of operations like 5 plus 2, when we don't know the final result, we have many models. And to give a couple of examples, one is increasing change, maybe the most classic, which is where we have a bag with 5 cubes, and we add 2 cubes, and we ask how many cubes there are at the end. Then again, it could also be a comparison problem. For example, it could be, let's say, I have a person, a child who is 5 years old, and another child who is 2 years older than the first. And we ask, how old is the second child? These 2 examples are clear, but we could also find combination problems or problems of the different types that we have analyzed from different contexts, which are related to this type of abstract calculation, like 5 plus 2 equals... And for operations like I'm missing 1 addend, but I know that when I add 2, it gives me 7, we can resort to the same models we have used for situations and context. Say, if my nephew is 7 years old and is 2 years older than my daughter, how old is my daughter? Or, I have some balls in a bag. I add 2, and now I have 7. How many balls did I have to start? It's exactly the same type of situation. With abstract calculations, we need to make the effort to associate them with a variety of situations. They can be for addition, but the missing number is the final or initial quantity, or they could be for subtraction. In the examples we propose here, we have a contextualized situation showing how 8 minus 3 equals an unknown result. The easiest thing is always to propose a context of decreasing change. A bus has 8 people, 3 people get off, how many are left? Or if I lack an initial number and have 8 minus something equals 5, a situation for this type of abstract calculation could be there are 8 people on a bus, some get off, now there are 5. How many people got off? The idea is to always work with different symbolic expressions and to help students by offering contexts so students can associate those symbolic calculations with the different contexts. In which situations is it appropriate for students to associate subtraction with counting up? Our end goal is that when we give students a subtraction problem, they can choose whether they want to solve the subtraction by taking away, counting backwards, or if they want to calculate the difference between the two numbers. In other words, we have two strategies to do 17 minus 2. I can do where we take 17 and then count backwards 2, which is 16, 15, or you could take the 2 and the 17 and count the jump I have to make to get from 2 to 17. Here, it's clearly more efficient to do the subtraction by counting backwards. But if the numbers I have are close, say we have a subtraction like 18 minus 15, it makes much more sense to do 15 and 18 and calculate the subtraction as a difference. How many do I have to jump from 15 to 18, right? Not take 18 and count backwards 15. So, if we want the students to have the flexibility to choose between one strategy or another, depending on whether the numbers are close or far apart, from the beginning, we have to give them different contexts and situations so they can try the two types. And so, for 17 minus 2, we can propose a situation. If I had 17 cookies and ate 2, it's clear that when I ate the first one, I had 16, and when I ate the second, I had 15, right? But on the other hand, to subtract 18 minus 15, I won't use the example that I had 18 cookies and I ate 15 of them. What I could ask is, I have a page in an album that has 18 spaces for stickers, and I've already put 15 stickers. How many stickers are missing? It's also a subtraction, but different because we have 15 and are missing 16, 17, 18, so we're missing 3. So, if I want to show that a subtraction can be done by counting down or counting up, I have to offer the students situations that invite them to use each method. And these situations have to be associated with numbers behaving in the correct way. If they are numbers, we say, that are far apart, or if the second number, the one we subtract, is small, we want them to count backwards. But if the numbers are close, we want them to look for the jump in between the two numbers.